Hello. At this point, you've learned how to make ethers, but in this video, we're going to learn how to make a very special cyclic ether called an epoxide. Now, epoxide is a general term for a three-membered ring that has oxygen as one of its members. So that's the simplest epoxide, and that is actually called oxirane. That's an official IUPAC name, but you could have groups coming off of either of those carbons, and I'll start using some stereochemistry as well. Let's see, what can I do? Whoops, maybe something like this. Okay. You could also have an epoxide off of a ring. The thing is, if you have a triangle, those two legs of the triangle have to be facing the same direction for it to meet up at the oxygen. And obviously, the other group could be dash, but I'll have a hydrogen here, and maybe a purple group there. Anyway, these are all epoxides. It's a class of molecules. How do we make epoxides? There are two ways. The first way is via a halohydrin. So let's say we have this alkene, and we do a halohydrin reaction, a reaction that you've all seen already. And we get this. The Br goes here, and the OH goes here. Okay. Now, the next step is to add a base, and it could be a weak base or strong base. It really doesn't matter. Let's add NaOH. And true, you could have substitution here. You could have elimination. That OH minus is a strong base, strong nucleophile. But the faster reaction is actually deprotonation. And let me draw the intermediate. Actually, I'll do the mechanism in just a bit. But pretend you have a O minus here. That is set up to attack this carbon and kick out bromine to give us our epoxide. Let me draw the mechanism. It is two reactions, starting from the alkene. Let me write that actually. Going to the first halohydrin, and then to the epoxide. Okay. Let's take a look at the mechanism. Now, the mechanism for this halohydrin formation you've seen before in the alkene unit, but I'll do it again here. Remember this, you're going to make the bromonium ion or the halonium ion. How do I want to do this? Okay, but then the weird thing is that this lone pair attacks back, typically the more substituted carbon, and we get this. And actually, let's use, maybe we could use some stereochemistry. So, for instance, let's say this is both wedge, and this bromine now is positive. We did create a Br minus, but we're not going to use that as the attacker. We're going to use water. Okay, water will attack the more substituted carbon, and we open up the ring. You should also remember that it was backside attack. So the water attacked from the dash, and you still have these two hydrogens attached. Now this one is still wedged, but because it's not a chiral carbon, you wouldn't know that once it starts rotating. Okay, good. And then finally, let's use water. We could also use the Br- to strip off this proton. Now, for my class, mechanisms, I don't usually ask for stereochemistry, but I'll just include it here because we included it in the previous steps. The thing is, sure, we have a dash OH here, but also half of the intermediates would have a dash dash, and that will end up giving us a wedge OH. Oh, we're not yet done. We have to now do the epoxidation, or the ring closing. So the thing is, we do need this bond because we have to show it breaking. Let's see. Okay, what's first? OH minus. We have base, NaOH. The real base is going to be the OH minus. We have this hydrogen here. Okay, this is going to be interesting because our O minus is still in the back. It's still in the back, and what's going to happen is it's going to attack this carbon here and do a substitution. Okay, it's an easy substitution because it's so close by, and remember this is at the back, so when this bond is made, that bond would also have to be from the back, or else the two bonds will not meet at the oxygen. This is an SN2 reaction, right? Backside attack, well, maybe that's not the important part. The important part is concerted. The attack and the leaving group leaving happens at the same time. And we have this isomer here. See, the oxygen is still dash on this carbon, but it also has to be dash on this dot, or else you wouldn't be able to close the triangle. We would get the wedge-wedge version also. So ultimately, you'd have a plus and it's an enantiomer. I didn't show any stereochemistry here, but that's the consequence of this SN2 reaction to close the epoxide ring. Okay? There's a second way to make an epoxide. Okay, how do I want to call this? This way is you cyclize the halohydrin. Cyclize. Cyclize the halohydrin. It is two reactions, like I said before. Is there a more direct way to make the epoxide? Yeah, it's using a peroxy acid called mCPBA, and I'll show you first what a peroxy acid is, and then we'll talk about the specific peroxy acid mCPBA. Okay, we'll call this epoxidation using a peroxy acid. So we know an acid, like a carboxylic acid. What is a peroxy acid? A peroxy acid will have, looks like a carboxylic acid, but it has an extra oxygen. Let me show you actually the reaction. Let us do, I don't know. Let's practice some stereochemistry. So for instance, what if we had that? Okay. If I use this peroxy acid, now, I would not write the word peroxy acid on the exam. I'll actually give the reagent, but for now, let's just say peroxy acid, and we have this. Well, the epoxide, again, has to be on the same side, the two legs, wedge-wedge, making this methyl group dash, and the other isomer is, dash-dash, making this one wedge. They are enantiomers. This is a racemic mixture. Okay, let me show you what a peroxy acid is and how we can see it on the exam. Peroxy acid, if you have an R group, it looks like a carboxylic acid, but it has this extra oxygen in there. You can see it abbreviated also as this, CO3H, not CO2H. Now, I don't want my students giving general compounds or general chemicals. I want them to give specific chemicals. So that R group can be anything. It could be a methyl group, and you could write it like this. Okay, that's a peroxy acid. The most popular peroxy acid, though, is this mCPBA. And you are allowed to give those letters if you're using this in the synthesis. But that is meta chloro per benzoic acid. So it's a benzoic acid, except it's a peroxy acid analog. So instead of an OH, we are going to put 2 oxygens more. Now you could draw it like this, or I've seen other sources draw it like that. Okay, but if you're going to use this, meta, and the chloro group is right here. That's actually called the meta position. If you're going to use this chemical, just write mCPBA. Okay. So these actually are the 2 peroxy acids that I typically use: the methyl peroxy acid and the mCPBA. Okay. What's happening? The mechanism is really interesting, I think, because honestly, which oxygen? So let's say, let's just use methyl, CO3H. Which oxygen is the one being added to the double bond to make the epoxide? It's actually a one-step reaction, or one concerted step. So let me have that, and it's actually this oxygen that's being delivered. So I want that oxygen right there, and then the rest of this you want to line it up. So, oh boy, am I lining this up? And then, okay, and then you have the methyl group. So this CH3CO3H is this one. CH3, CO3, and then the H. Okay, so here's the mechanism. It's really interesting. This one picks up the H, this oxygen, by using the electrons of the pi bond. Then this bond goes here, delivers this oxygen, but this bond has to come back and hit the oxygen, so now we have 2 legs of the triangle, and then this one goes here. One step. So if you follow everything, let's draw the epoxide first. We have this oxygen like that. Okay, what happened to the rest of this stuff? So we had this 2-carbon piece right here, and I said that this oxygen picked up the hydrogen using a pi bond. So now it's a single bond. And do you see how this bond goes here to make a double bond to the oxygen on the left? So we end up with a carboxylic acid, and here's your epoxide. I think that's it. Let me give you another example, because I want us to get used to seeing some stereochemistry on the epoxide, because that's going to be very important when we start using epoxides for reactions. So again, this is the Cyclize halohydrin from an alkene. But you know what? I would rather just use one step or one reaction to get to the epoxide from an alkene again, using peroxy acid. I would prefer using the peroxy acid. Okay. Let me give a couple more examples. Here we see an example of stereochemistry. But what if we draw the molecule like this? Like that. Okay? And then we do mCPBA. Is it really important how we draw wedges and dashes on this molecule? It is. And what I would do is I would make this kind of flat like that, and realize that now these two methyl groups are on opposite side. So I'm going to do this, and I'm going to do that. And I'm going to put the oxygen on top. So that's one way to draw the epoxide showing stereochemistry. Now the thing is, yes, what if it came from the bottom? So if it came from the bottom, we still have our two methyl groups facing opposite each other. So I know they're both going up, but one's coming towards us and the other one's going away from us. And we have this oxygen right here, like that. Okay. Now you may ask yourself, are these identical? Let's check. So on this chiral carbon, that is chiral, we do have the hydrogen that is dash. So it goes oxygen, then this carbon, then this carbon. So this is definitely R. This is definitely R. Now if I look at this one, our hydrogen is now wedge, so that's pointing in the wrong direction. But the priority goes 1, 2, 3. It is S, but it's pointing in the wrong direction, so we take the opposite. It looks S, but it's actually R. That's interesting, because the possible isomer of this, the enantiomer, I bet that this is S, and this is S. We mirrored both chiral carbons. Okay, and you can check for yourself. You decide, or you assign priorities, and you double check whether these two are actually S's. So that's another way to show stereochemistry, where not the legs of the triangle have wedges and dashes, but the groups on the chiral carbons do. Do you see the difference? Here I drew wedges and dashes on the substituents, but over here I drew dashes and wedges on the actual epoxide part. The actual epoxide part. Think about that. Those are two different molecules. This is racemic, and this is racemic, and they're different. It's a 50-50 mixture. But imagine if I had drawn this alkene and did mCPBA. Again, how do you want to start? Start like this. Okay? And you have a wedge here, a wedge here. Now, if you feel a little uncomfortable interpreting that, you do have a dash hydrogen and a dash hydrogen. So look how this looks tetrahedral, right? Each of those two chiral, maybe not chiral. No, they are chiral. Each of these two chiral carbons. But my question is this the same molecule or different? If I put the oxygen down here. Because when I did it here, we definitely got a different molecule. RR and SS. Why didn't you figure out the stereochemistry? Or, even better, make models. Or, just as good, rotate the molecule on, for instance, the right. Rotate this in your head and see if it's identical or not to this molecule here.